Okay, welcome back, Honors Kim. Today, this is our lesson. Had we been in school on Thursday, March 19th? Um, so let's go over the do nows for that. Uh, we're going to be going over two things today. We're still continuing on with colligative properties. Today, we're going to look at boiling point elevation. So we have a chart here that we're going to look at here in a little bit, and then we have an assignment which you will have due tomorrow. Your homework for today was to complete solution stoichiometry number 2. That one I was collecting, and so make note of that. We will deal with that at a later time, as I have said before. But I was collecting that. Make sure that you check the answer key that is posted on as a link to my Canvas homepage. Make sure you do that. So we're going to talk about boiling point today. You'll have a homework assignment, as I said, that's due tomorrow. I would like to make mention of this again. I know I've already mentioned it, but I would like to say it again. So originally, had we been in school, I assigned this mastering chemistry on Tuesday the 17th. It was to be due this Friday, March 20th, which according to this would be tomorrow. However, based on the fact that, again, Dr. Hanback directed that this week is an extension of spring break, that you were not obligated to do any work this week if you didn't want to, that I have extended this due date. And although it says March 20 here, it is actually due on Friday, April 3rd. All right, so that will be noted once you click on the mastering assignment. You will see that although it was opened on the 17th, it was not due on the 20th, but in fact April 3rd. But I want to leave this as it was because, again, this is the way things would have been had we been in school. So that takes care of that. So let's go to our notes and today's lesson. So again, as we talked about yesterday, I'll start with the two colligative properties we talked about yesterday, and that was vapor pressure and osmotic pressure. When you add a solid to a solution, or to water, I should say, or to any other solvent and form a solution, what you now have is a reduced quantity of solvent in a given volume, because a lot of the solvent molecules now are bonded, attracted to the solute particles, and so there are fewer free solvent molecules or water molecules able to vaporize. So as a result of that, vapor pressure goes down, and so vapor pressure and solution concentration are inversely related. On the other hand, in regard to osmosis and osmotic pressure, the greater the solution concentration, the more water is going to move through a semi-permeable membrane to the side of higher solute concentration, which is the side of lower solvent molecule concentration. And so as you do that, and as your solution is more concentrated, then osmosis increases, and the amount of pressure required to stop osmosis increases as well. So osmotic pressure and solute concentration are directly proportional. As a result of that, I mentioned yesterday, or as a result of vapor pressure changes with solute concentration, what ends up happening is that water is a pure solvent and normally freezes at 0 and boils at 100. But with a vapor pressure change, those numbers change. And in fact, this range where water is normally a liquid gets extended when it becomes a solution. And so today we're going to talk about this half of the extension, which is the fact that its boiling point goes higher. We call that boiling point elevation, which is what we start with right here. So pure water, again, normally boils at 100 degrees, but the addition of 1 mole of any non-electrolyte solute particles to 1 kilogram of water, which then is a 1 molal solution. Remember, molality is moles of solute per kilograms of solvent. We'll raise, and again, this says any, all right? Remember, colligative properties don't really rely on the identity of the solute, it's just how much of it is in the solution. will raise the boiling point of pure water by a little over a half a degree, 0.512 degrees Celsius. This is called the mole boiling point constant, or KB, for water. So let's look at this handout that you were to pick up today. And the top chart is what we're looking at today. These are boiling point constants, or KBs, for various solvents. I have water listed first. It is 0.512 degrees Celsius per mole. And I listed a couple other solvents underneath there: ethanol, benzene, cyclohexane, acetic acid. And you can see their values as well. Again, those values relate to the Lewis structures of those solvents, intermolecular forces, etc. So that is that. Then, so there's a KB for various other solvents, so you would refer to those there. So here is how molality then affects boiling point. This is the change in boiling point equation based on the molality of a solution. This is the change in the boiling point temperature, okay? Delta T BP is equal to the boiling point constant, KB, times the molality of the solution, all right? Times the molality of the solution. So this is the change in the boiling point, not the new boiling point. If water is the solvent, then once you calculate the change in the boiling point, you would add that number to water's normal boiling point, which is 100. Again, based on this, when you add a solute to water, its boiling point temperature increases. So this is the change in that boiling point temp, and you would then add it to its original boiling point to get the new boiling point of the solution. So the new boiling point temp is equal to the original boiling point temp plus the change in the boiling point, which we calculate there. Okay. Now, if this is water, then that original is 100 degrees Celsius. If it is some other solvent besides water, then I would give you that solvent's original boiling point. Okay, and I think on your homework there's at least one, if not two, problems that involve a solution whereby water is not the solvent. So you would need to make sure that you're using the KB for that solvent, and you would also need to know the original boiling point of that solvent, which I would give you. Okay, so let's look at some examples of that. Tried to go to the corner again, Mr. Schaff. Dang, old habits are hard to break, especially for this old guy. Okay. First example. What is the boiling point of a solution? So we are looking for then the new boiling point temperature, okay, that has been made by dissolving 255 grams of glucose, that is our solute, all right, in 825 mLs of water. So water is our solvent, all right? So again, that needs to be in kilograms in regards to molality. And so with water being the solvent, again, the conversion from mLs to kilograms is essentially the same as grams to kilograms, which is dividing by 1,000 or moving the decimal 3 to the left. So we have 0.825 kilograms of water. So before we determine the new boiling point temp, we need to know the molality of this solution, because that's what's going to determine the change in the boiling point. So we do not have molality yet, so we're going to have to get to it. This is why we reviewed molality calculations the other day, actually yesterday. So first we need to know the number of moles of our solute. Our mass is 255. So we need the molar mass of our solute, which is glucose, which would be 72, 12, and 96, which is 180 grams per mole. So 255 over 180. And again, we're not rounding yet. 1.41, 6 sixes, and a 7, which is as many decimal places as my calculator goes out. So there's that. Again, no rounding yet. So then to find the molality of the solution, we take that number of moles, 1.416666667, and divide it by the kilograms of our solvent, water, 0.825, and that. Now, on your homework, I asked you to calculate molality, and in other words, I asked for an answer for that calculation. So based on that, we would round the molality. I didn't do that here, but since we did it on the homework, I'm going to go ahead and do that here. So based on our data, we would round this molality to 3 sig figs, 1.72 molal. Now we can determine the change in our boiling point based on the molality of this solution. So the change in the boiling point temp is equal to Kb, the boiling constant, times the molality. Kb you pull from the chart for water. That is 0.512. Our molality is 1.72. And so we multiply that. Again, we will round to 3 sig figs, 0.881 degrees Celsius is the change in our boiling point. Okay, so the new boiling point temp would be water's original boiling point as a solvent, which is 100 plus 0.881. Now, we are not going to round this down to the whole number because this is a constant. This boiling point temp is a constant for water at standard pressure. And so we are going to keep this at the 3 decimals just as it is now. So the new boiling point temperature is 100.881 degrees Celsius, or almost 101. All right. So applications of boiling point. Probably you've seen your mom or your grandma or maybe even yourself when you cook pasta. What do they usually do when they put water on the stove before they throw the pasta in there? Of course, they heat it up. What do they usually throw in there? Well, my grandma always threw salt in there. I thought, now, is she doing that to make it more salty? No. She's doing that to raise the boiling point temperature of the water, which is now a solution. And so what that means is your water is boiling at a slightly elevated temperature higher than 100, which means your pasta is cooking faster as it's boiling because it's boiling at a higher temperature. So why is that important? Well, the longer you boil pasta or the longer you cook pasta, the gooier and the mushier it gets. So you want to get it cooked as quickly as you can. So this is a little cook's trick in order to do that. But it's a nice little cook's trick based on chemistry. All right. Here's another application. We use antifreeze in our radiator in summer. All right. Why do we do that? Well, let's see. If we had pure water in our radiator, which you could have, that water is going to boil at 100 Celsius or 212 Fahrenheit. Well, the amount of heat given off by your engine during combustion is going to drive the temperature of that water well over 212 degrees. In fact, a lot of you probably have a little temperature gauge in your on your dashboard, and that thing goes over 212. If all you got in there is water, you're boiling over and you're stranded. All right. So we add a solute to that water. In the case of antifreeze, antifreeze is a great solid because number one, it's easily made. It's quite plentiful. It's fairly inexpensive, and it also has some additional qualities to it that keep the inside of your radiator from rusting, keeps it clean, keeps the solution moving through there very well. So it's got a lot of advantages to using it. When you add that antifreeze to your water in the radiator and you make a solution, you are driving up the boiling point. All right, which means if the water or if the solution gets to a temperature based on your engine running, upwards of 220 or 225 degrees, it's not going to boil over because the boiling temperature has been driven higher than what it normally is. So there's another advantage to that. We utilize that on a regular basis. Excuse me. So let's do the other example here. This one's a little different. We're actually going to kind of work backwards from what we did on the first one. So the boiling point of a solution that was made by adding ethanol to water is 101.25 degrees. So this is the boiling point of the solution, all right? Which means this is the new boiling point temperature. All right? First question is, what's the molality of the solution? Well, remember, molality is moles over kilograms. We don't have moles. We don't even have kilograms yet. So can we find molality? Yes, we can, because the relationship here between the change in the boiling point temperature and molality and the boiling point constant for the solvent, in this case water, we can use that equation to determine molality. So the change in the boiling point temp is equal to Kb times M. Well, we need the change in the boiling point. This is the new boiling point of the solution. So what does water normally boil at as a pure solvent? 100. So the change in the boiling point then would be 101.25 minus 100, which is 1.25 degrees Celsius. That is the change. Again, we're not going to be rounding that. That's a constant. It's an intermediate calculation anyway. So here's the change. That goes here. The Kb for water, we look up on the chart, 0.512 times the molality. So if we divide out 0.512, then the molality of this solution to 3 sig figs, according to that, is 2.44 molal. 2.44. Now, what mass of ethanol, so we're looking for the mass of our solute now, has been dissolved in the solution if there are 1,252 mLs of water in it. So water is the solvent, as we said before. It needs to be in kilograms. And so again, we can just move the decimal 3 to the left or divide by 1,000, 1.252 kilograms. I would remind you again, if this problem had involved a solvent other than water, number one, this Kb would not have been 0.512. It would have been a different number. We would have had to use it here. Number two, if this was an ml, a volume of a different solvent other than water, then that means its density is not 1. I would have given you that solvent's density. You would have had to use that to calculate the grams of that solvent from its density and then convert it to kilograms. We've done that before when we studied molality in Unit 10.1. That definitely could come up again, all right? Here it does not. So first things first, we have the molality, we have the kilograms, we can get the moles of our solid. So we have M equals N over kilograms. Molality is 2.44, N over 1.252. So we put a 1 under the 2.44 and cross multiply this thing. So we have N equals 2.44 times 1.252. And again, we will not round this because this is an intermediate calculation, 3.05488 moles. And now we can find the mass of our ethanol by utilizing the relationship between mass moles and molar mass. So we have the moles, 3.054 That's right there. 488 equals M over, okay, ethanol is our solute, C2H5OH. Hopefully you remember that from organic. So that would be 24, 5, 16, and 1, which is 46 grams per mole. So M over 46. Again, we can put a 1 under there, cross multiply it. So M equals 3.05488 times 46. And to 3 sig figs, 141 grams of ethanol. So basically, if we work back the other direction, we can say if we dissolve 141 grams of ethanol in 1,252 mLs of water, we will get a solution that has a molality of 2.44 molal, which will then raise the boiling point of that solution up to 101.25 degrees. Okay, that concludes today's lesson on boiling point elevation, which is the third colligative property. Again, it is based on molality. You have an assignment that you got picked up or have for today. That will be due tomorrow, so we'll be working on that. Again, you can check the answer key that's posted at my Canvas homepage to make sure you're doing everything correctly. If you have an issue, shoot me an email and I'll help you with it. So until next time, this is Mr. Keister signing off. Take care of yourselves and I'll see you soon.